Welcome to the presentation on designing distributed systems. In this session, we will explore the key principles, challenges, and the CAP theorem that drive the architecture of distributed systems. Let's dive in. Here's the agenda for today's presentation. First, we will look at the key principles and challenges of distributed systems. Then we will explore the CAP theorem, followed by strategies for designing distributed systems. We will also discuss the common challenges in distributed system design. Finally, we will summarize the key takeaways. Let's begin with the key principles of distributed systems. Decentralization. A distributed system does not rely on a single central authority, which makes it more resilient but introduces coordination challenges. Communication and coordination. Nodes in the system need reliable communication despite potential network issues like latency or message loss. Fault tolerance. Distributed systems need redundancy and failover mechanisms to ensure the system can recover from node failures. Scalability. To handle large volumes of users or data, distributed systems can scale both horizontally, adding more machines, and vertically, adding resources to existing machines. Distributed systems face a variety of challenges. Consistency issues. Maintaining synchronized data across distributed nodes can be complex, especially in real-time applications. Security concerns. Since data is spread across multiple nodes, securing the communication channels and protecting against unauthorized access becomes crucial. Latency and throughput. Ensuring low latency and high throughput across distributed systems, especially with large data, can be challenging. The network can often become a bottleneck. Now let's talk about the CAP theorem, which is a fundamental concept in distributed systems. According to this theorem, a distributed system can provide at most two of the three guarantees. C for consistency. Every read will return the most recent write. A for availability. Every request will get a response, even if it's not the latest data. P for partition tolerance. The system will continue functioning even if there is a network partition or communication failure. Understanding these trade-offs is crucial when designing a distributed system. Let's break down the trade-offs based on the CAP theorem. CP. Consistency plus partition tolerance. Systems like Tabspace or Zookeeper prioritize consistency and partition tolerance but may sacrifice availability during network partitions. CA. Consistency plus availability. This setup guarantees both consistency and availability, but it fails to handle network partitions, making it less feasible for distributed systems. AP. Availability plus partition tolerance. Systems like Cassandra or Couchbase prioritize availability and partition tolerance, but they may not always be fully consistent, often relying on eventual consistency. Designing distributed systems requires strategies to handle challenges like network failures and scaling. Replication and redundancy. By creating multiple copies of data across different nodes, we ensure availability even in the event of a failure. Consistency models. Depending on the needs of the system, we can either opt for eventual consistency or strong consistency. Consensus algorithms. Algorithms like Paxos and Raft are used to help nodes agree on decisions even if some nodes are unavailable. Data partitioning and sharding. Data is partitioned horizontally or vertically to scale the system and reduce bottlenecks. Load balancing. We use load balancers to distribute requests efficiently across multiple servers. In addition to the core design principles, there are several strategies that can help optimize distributed systems. Fault detection and recovery. Systems should be able to detect node failures quickly and recover from them without significant downtime. Eventual consistency. In some cases, it's acceptable to have temporary inconsistencies in data which can be resolved later. This is often used to improve system availability. Distributed transactions. Complex systems may require techniques like two-phase commit or saga pattern to ensure transactions across multiple nodes are consistent and reliable. When designing distributed systems, we also need to address the following challenges. Network partitioning. Communication failures between nodes can occur, so the system should be resilient and handle network partitions effectively. Eventual consistency. Managing temporary data inconsistency can be tricky, especially when handling conflicting updates. Distributed transactions. Coordinating transactions across different nodes introduces complexities in ensuring atomicity, consistency, and reliability. To summarize, designing distributed systems is a complex task that involves making trade-offs between consistency, availability, and partition tolerance, as defined by the CAP theorem. Key design considerations include fault tolerance, scalability, and consistency models. It's crucial to plan for network failures, replication, and load balancing to ensure the system performs efficiently and is resilient to failures. That concludes our presentation on designing distributed systems. I hope this has given you a clearer understanding of the principles, challenges, and design strategies. I will now open the floor to any questions you may have. Hello and welcome. In this presentation, we will explore the concept of high availability in system design, diving into key principles and best practices for ensuring that systems remain operational with minimal downtime. High availability or HA is a design approach that ensures systems are continuously available and operational, even in the event of failures. The main goal is to minimize service disruptions, providing users with uninterrupted access. To achieve HA, we focus on fault tolerance, load balancing, replication, and failover mechanisms. In system design, we will often encounter two main configurations, active-active and active-passive. In an active-active configuration, multiple systems run in parallel, sharing the load and ensuring continuous service. In an active-passive configuration, one system is active while the other is passive, such standby, ready to take over in case the active system fails. Choosing between these configurations depends on our system's specific needs for performance and redundancy. Load balancing is crucial in any high availability system. It helps distribute incoming traffic across multiple servers to prevent any one server from becoming overwhelmed. There are different methods for load balancing. Round robin distributes requests evenly. List connections routes traffic to the server with the fewest active connections. IP hash routes traffic based on the client's IP address. We can choose from hardware-based, software-based, or cloud-based load balancers depending on our system architecture. Replication ensures that data is copied and stored across multiple systems, ensuring redundancy and availability. There are two common types of replication. Master-slave. The master system handles both read and write operations, while the slave systems replicate the data. Master. Both systems handle reads and writes, providing better load balancing. It's important to keep an eye on replication lag, which is delay between when data is written to one system and when it's replicated to others. Sharding and partitioning help scale our database to handle large amounts of data and traffic. Sharding this divides our database into smaller pieces called shards and distributes them across multiple servers. Horizontal partitioning sharding splits the data by rows, such as dividing users by region. Vertical partitioning divides the data by columns, such as separating user data from transaction data. Distributing services across multiple geographic regions can significantly enhance availability. Multi-region deployments help reduce latency by routing users to the nearest data center. It also improves fault tolerance, as failure in one region does not affect the availability of services in other regions. For example, traffic can be routed to data centers in the US, Europe, and Asia, ensuring that users from different parts of the world have fast access to services. Failover is a process of switching to a backup system when the primary system fails. Automatic failover happens without human intervention, ensuring minimal downtime. Manual failover requires intervention from administrators during a failure. Key components from implementing failover include health monitoring and automated traffic rerouting to backup systems. Health monitoring is essential to detect and respond to failures promptly. Heartbreak mechanisms check the status of systems at regular intervals. Health checks to help monitor the availability of services, databases, and instances. If a failure is detected, the system can promote standby systems to take over without manual intervention. Disaster recovery ensures that systems can recover after a catastrophic event such as a server failure or data loss. Key elements of DR include data breakup, data backup, regularly backing up data to avoid data loss, failback procedures, returning to the primary system once it's recovered, geographic redundancy, storing backups in different regions to avoid localized failures. To design highly available systems, there are several tools and technologies we can leverage. Cloud providers like AWS, Azure, and Google Cloud offer built-in availability features such as elastic load balancing, auto-scaling, and multi-region deployment. Database solutions like Amazon RDS, Google Cloud Spanner, and Cassandra ensure high availability and scalability. Content delivery networks (CDNs) improve availability by caching content across multiple global servers. In summary, designing for high availability is about ensuring that our system remains online with minimal downtime. Key strategies include active-active configurations for better load distribution, data replication and sharding for redundancy and scalability, failover mechanisms and health monitoring to handle system failures, leveraging cloud services and CDNs for global availability and resilience. That concludes the presentation on designing for high availability. Thank you. Welcome to day 31 of our course. Today we will be diving into caching techniques in high-level designs. This session will cover the fundamentals of caching and its roles in optimizing system performance and scalability. Let's start with the basics. What is caching? Caching refers to storing frequently accessed data in a quick access storage system, allowing us to retrieve it faster than querying the original data source every time. So, why does caching matter in high level design? Caching reduces the load on databases and speeds up response times for end users. It also enables horizontal scaling by offloading repetitive tasks from the primary system. Now let's talk about distributed caching systems. These systems span multiple machines or nodes, ensuring that the cache can handle high loads and remain available even if some parts of the system fail. Popular distributed caching systems include Redis, Memcached, Apache Ignite, and Amazon Elastic Cache. Redis, for example, is an in-memory data structure stored with support for persistence and replication, while Memcached is known for its simplicity and speed, though it does not support persistence. Distributed caching provides several benefits. Among them, reduced latency, offloading the backend, and scalability are the mentions. Reduced latency as the data is stored closer to where it's needed. Offloading the backend by reducing the number of database queries. Scalability because distributed caching systems can easily scale horizontally to meet increased demand. Cache evictions are an essential part of caching, determining when data should be removed from the cache. Without an eviction policy, caches can become too full and inefficient. There are several common cache eviction policies. LRU, least recently used, evicts the least recently accessed data. LFU, least frequently used, evicts the least frequently accessed data. FIFO, first in first out, evicts the oldest data first. Random eviction randomly removes data. TTL, time to live, automatically expires data after a set time. Let's dive a deeper into these eviction policies. LRU is ideal for general purpose caching where recent data is more likely to be needed. LFU works well in systems where certain data is accessed far more frequently than others. FIFO is simple and effective, though it may not always keep the most useful data. Random eviction can be useful in scenarios where simplicity is key. TTL ensures that cache data does not grow stale and is particularly useful for time-sensitive data. Choosing the right eviction policy depends on your system's need. Factors to consider include data access patterns like how often the data is accessed and updated, performance requirements including the need for low latency and high throughput, consistency requirements such as whether data freshness is critical. For example, if we have a high read low write system, LRU might be a good choice while TTL is perfect for temporary data. Let's now move on to caching strategies. There are several approaches for integrating caching into our system. Cache aside or lazy loading, the application fetches data and stores it in the cache when necessary. Read through, data is fetched from the data stored if it's not in the cache. Write through, both the cache and data stored are updated simultaneously. Write behind, updates are written to the cache first and then asynchronously to the data store. Cache invalidation, this strategy ensures that outdated data in the cache is removed or updated when the underlying data changes. When designing our cache in HLD, it's crucial to follow best practices. Cache only expensive data. Focus on caching data that is slow or costly to retrieve. Avoid cache stamp tests. Prevent multiple clients from simultaneously refreshing the same data. Use multiple cache layers. Utilize both local and distributed caches. Set expiration carefully. Use TTLs that balance freshness with performance. Monitor cache performance. Keep track of hit or miss ratios and eviction rates. Let's look at caching in action with a real world example. In an e-commerce site, product details, user sessions, and frequently queried data are cached for better performance. For example, Redis can be used for storing sessional data, while Memcached can be used for caching product catalog data. The LRU eviction policy might be used for session data, and TTL can be applied to product details to ensure they stay up to date. In conclusion, caching is a powerful technique for optimizing system performance and scalability. By choosing the right distributed caching system, eviction policy, and caching strategy, we can significantly improve the efficiency of our systems. Remember, successful caching requires careful planning and monitoring. Thank you for your attention. This concludes our session on caching techniques in high-level design. Welcome to today's presentation on data partitioning and sharding. In this session, we will explore how data distribution can be scaled and optimized to enhance database performance, ensuring scalability and efficiency in large-scale applications. Today, we will cover the essential concepts of data partitioning and sharding. Our goal is to understand how these techniques help scale databases. We will begin with an introduction to data partitioning, followed by an exploration of various sharding strategies and best practices to ensure effective data distribution. Data partitioning is the process of splitting large datasets into smaller, more manageable pieces. This technique is crucial for reducing the load on a single server, improving both performance and scalability. There are three primary types of partitioning: horizontal partitioning, vertical partitioning, and directory-based partitioning. Each method serves a unique purpose based on system requirements. Let's dive deeper into the types of data partitioning. Horizontal partitioning or sharding involves dividing rows across multiple servers, ensuring efficient data distribution. Vertical partitioning, on the other hand, involves splitting a table's columns, which helps separate frequently accessed data from less used data. Finally, directory-based partitioning uses a directory to track data locations, offering scalability in how data is distributed across servers. Sharding is a special case of horizontal partitioning where data is distributed into smaller shards. The goal is to scale the database by placing data across multiple servers. The sharding key plays a vital role determining how data is distributed across the shards, ensuring an even spread to avoid performance bottlenecks. There are several strategies for sharding data. A range-based sharding divides data into specific ranges like user IDs from 1 to 1000, while effective for range queries, it may result in hotspots. Hash-based sharding uses a hash function to distribute data evenly but may not support range queries efficiently. List-based sharding assigns data to predefined lists, which works well for group data but might cause uneven distribution. Sharding comes with its own set of challenges. Rebalancing is crucial to ensure that data remains evenly distributed as the system grows. Cross-shards joins can lead to inefficiencies and performance degradation. And of course, handling failures is essential. Having robust data replication and backup mechanisms is critical to prevent data loss. Sharding and partitioning are widely used in various industries. In e-commerce systems, data might be partitioned by user region or order ID. Social media platforms often shard data based on user ID or geographical location. Financial applications may partition data by customer or transaction ID to ensure efficient data access and management. Efficient sharding and partitioning require careful planning. Choosing the right shard key is vital to ensure even distribution of data. Cross-shard queries should be minimized to improve efficiency. It's important to plan for rebalancing as our data grows and to implement replication for high availability. Finally, continuous monitoring is essential to optimize system performance and ensure scalability. Several tools can help implement sharding and partitioning strategies effectively. Cassandra, a NoSQL database, excels in horizontal scaling. MongoDB also supports sharding for large datasets. MySQL with its NDB cluster distributes data across nodes for high availability, while CockroachDB automatically partitions data across multiple locations. In conclusion, data partitioning and sharding are critical techniques for scaling large-scale applications. Selecting the right partitioning method, shard key, and ensuring robust failure handling is key to successful implementation. Tools like Cassandra, MongoDB, and MySQL can help streamline the process, enabling our system to scale efficiently and reliably. Thank you for your attention. This concludes the presentation on data partitioning and sharding. If you have any questions or would like further clarification, feel free to ask. I would be happy to discuss any aspect in more detail. Hello everyone and welcome to this presentation on API Gateway and Service Mesh, key components in modern system design. In today's session, we will explore the core concepts, responsibilities, and key features of these two important components in building scalable and secure microservice architectures. Let's take a look at the agenda for today. First, we will introduce the concept of API Gateway and discuss its responsibilities. Then we will move on to Service Mesh, dividing it to its core features. We will also compare API Gateway and Service Mesh, explore best practices for each, and conclude with a summary of their roles in modern system design. An API gateway is a server that acts as an entry point for clients to access various backend services. It handles traffic routing, authentication, and other responsibilities such as caching and rate limiting. Think of it as a traffic controller managing how requests flow from external clients to the right services within our system. Now let's dive into the key features of an API gateway. First, it routes incoming requests to the correct backend services. It's also responsible for centralized authentication and authorization, ensuring that only authorized clients can access our services. Additionally, it can implement load balancing, distribute traffic, cache data, and enforce rate limiting to protect backend services. There are several popular API gateway tools available. Kong is an open source solution that offers plugins for traffic management and security. Nginx is a lightweight, high performance gateway that works well for web applications. AWS API Gateway is a fully managed service for building and deploying APIs, and Traffic is another modern HTTP reverse proxy focused on microservices. Now, let's turn our attention to service mesh. A service mesh is an infrastructure layer that manages service to service communication within a microservices architecture. Unlike the API gateway, which focuses on external traffic, a service mesh handles internal service communication, ensuring reliability, security, and observability. Some key features of a service mesh include service discovery, which automatically detects services and their instances. It also provides traffic management, ensuring that requests are routed appropriately. Load balancing, fault tolerance mechanisms like retries and circuit breaking, end-to-end security with manual TLS, and observability for tracking service interactions are all integral to a service mesh. Some widely used service mesh tools include Istio, which is feature rich and offers robust traffic management and observability. Linkard is another popular choice, known for its simplicity and lightweight architecture, and Consul by HashiCorp focuses on service discovery and configuration. Now let's compare API gateway and service mesh. The table on this slide outlines some key differences between the two. API gateway manages external traffic, including routing, security, and caching, while a service mesh focuses on managing internal service communication. Both play important roles but serve different purposes within a microservices architecture. To maximize the effectiveness of our API gateway, it's important to decouple concerns by using the API gateway solely for external communication. Ensure that it scales well with increasing traffic and implement strong security measures such as authentication and encryption. Finally, avoid overloading the API gateway with too many responsibilities, keeping it focused on its core tasks. Similarly, for service mesh best practices, ensure efficient traffic management by leveraging dynamic routing and traffic splitting. Always prioritize security with manual TLS and make observability a priority by implementing robust logging and tracing. Enforce strict access control policies to ensure secure communication between services. In conclusion, both API gateway and service mesh are crucial components in modern system design. The API gateway serves as the entry point for external client communication, while the service mesh handles internal service communication. Together, they ensure a secure, scalable, and efficient architecture for microservices. Thank you for your attention. I am now open to any questions you may have. Feel free to ask about API, gateway, service mesh, or any other related topics. Welcome to the presentation on fault detection and circuit breaker patterns. Today we will dive into these key concepts and how they help ensure robustness in distributed systems. In this session, we will explore three main topics: fault detection in distributed systems, the breaker pattern for fault tolerance, and how we can combine these patterns to enhance system resilience. Fault tolerance refers to the process of identifying when a service or component fails or experiences degraded performance. It's a crucial part of maintaining a reliable system. By detecting faults early, we can take actions before the issue affects the end user experience. There are several techniques for detecting faults in a distributed system. Health checks are used to monitor the system's liveliness, readiness, and startup status. Heartbeat mechanisms send periodic signals to indicate service health. Timeouts and retries ensure that requests don't stall infinitely. Monitoring and logging tools like Prometheus and Grafana help track system performance, while dependency analysis can identify potential issues based on inter-service dependencies. Effective fault tolerance helps prevent cascading failures where one service failure leads to a domino effect across the system. It also improves overall system reliability by avoiding early warnings for potential issues. Moreover, continuous monitoring tracks performance trends, allowing for proactive maintenance and scaling. The circuit breaker pattern is a fault tolerance mechanism that helps stop requests from being made to a failing service. Much like an electrical circuit breaker prevents overloads, this pattern isolates failing services to avoid overloading them and causing further disruptions. Circuit breakers function through three stages: closed, open, and half open. In the closed state, the service operates normally. When a failure is detected, the circuit breaker switches to the open state, preventing any further requests. After a set time, it moves to the half-open state where limited requests are allowed to test if the service has recovered. If successful, the circuit breaker closes again, otherwise it remains open. The circuit breaker pattern provides several key benefits. It prevents cascading failures by isolating issues before they spread, improving the resilience of the overall system. It also protects system resources by stopping unnecessary requests to failing services, allowing time for recovery. Several tools help implement the circuit breaker pattern. Histric is a popular Java-based library, while Resilience 4j is a lightweight alternative that supports additional resilience patterns. Istio, a service mesh, provides circuit breaker functionality in microservice environments, making it easier to manage fault tolerance at scale. Fault detection and circuit breakers work together to enhance system resilience. Fault detection identifies failing services, while the circuit breaker patterns prevents overloading those services, ensuring that the system remains stable. For example, in a payment gateway scenario, health checks could trigger the circuit breaker to isolate the failure and maintain service availability. To effectively implement fault tolerance, use granular fault detection methods such as service level health checks. Adaptive timeouts ensure requests don't hang too long, and exponential backoff reduces retry rates to avoid overwhelming services. Fallback strategies allow the system to provide degraded functionality when a service fails, and automated recovery ensures minimal human intervention in transitioning states. In summary, fault detection helps us identify issues early in the system. The circuit breaker pattern prevents cascading failures by isolating faulty services. When combined, these two patterns enhance system robustness and ensure reliability even during failure scenarios. That concludes the presentation. I hope you have a better understanding of fault detection and circuit breaker patterns. I now welcome any questions you may have. Welcome to this presentation on queuing systems and message brokers. Today we will explore the fundamentals of message brokers like RabbitMQ, and Kafka, their importance in system design, and how they help create scalable and resilient applications. In this session, we will cover several important topics, starting with an introduction to message brokers. Then we will dive into the key concepts behind RabbitMQ and Kafka, two popular message brokers. We will also discuss how these systems fit into high-level design along with design patterns and best practices. Finally, we will conclude with a summary of the key takeaways. Message brokers are intermediaries that enable communication between decoupled services using asynchronous messaging. This allows systems to be more efficient, reliable, and scalable. Key features of message brokers include enabling asynchronous communication, decoupling services, ensuring reliability and fault tolerance, and providing scalability for handling large volumes of data. Let's now look at RabbitMQ, which is a traditional message broker that follows the AMQP protocol. RabbitMQ uses key concepts such as queues to store messages, producers to send messages to queues, and consumers to process those messages. Exchanges route messages to queues and binding link exchanges to those queues. RabbitMQ is widely used in scenarios like task queries, workload distribution, and request replay patterns. Next, we have Apache Kafka, a distributed messaging system that excels at high throughput and real-time event streaming. Kafka's core components include producers who publish messages to topics, consumers who subscribe and process messages, and partitions that divide topics to enhance scalability. Kafka is great for event streaming, log aggregation, and building data pipelines. Queuing systems play a crucial role in high-level design by facilitating asynchronous communication between services. They help with load balancing and scalability by distributing workloads across multiple consumers. Additionally, they ensure fault tolerance, ensuring that messages are not lost, and allow for rate limiting and throttling to prevent system overloads. There are several design patterns used in message brokers, including the publish subscribe pattern, where messages are broadcast to multiple consumers, the work queue pattern, which distributes work across multiple consumers, and the competing consumers pattern, where multiple consumers compete to process messages from the queue. These patterns are essential for building scalable, resilient systems. To implement message brokers successfully, several best practices should be followed. Ensure that messages are idempotent, meaning they can be processed multiple times without side effects. Use message acknowledgement to confirm that messages are processed successfully. Implement dead letter queues for failed message processing. Monitor the performance of our brokers and handle backpressure effectively to manage high message inflows. To summarize, queuing systems and message brokers are essential for building scalable, resilient, and decoupled systems. RabbitMQ is ideal for traditional message queuing, while Kafka excels in real-time event streaming and high-throughput applications. By following best practices like idempotency, acknowledgement, and monitoring, we can ensure that message systems remain reliable and effective. Thank you for your attention. That concludes our presentation on queuing systems and message brokers. I now welcome any questions or discussions you may have.